So we are starting a new course, and this new course is Introduction to M theory, and we will have it's a joint course with Tomoki Nosaka, and the first half I will give 2 lectures per week, and in the second half of the semester Tomoki would give 2 lectures per week. So it's kind of a double course. Now, despite time is running, I would like to devote the first talk to kind of considerations what this course is all about and what is this business all about. Because like 15 years ago, when I was giving, when I was preparing to give a colloquium for students, one student just at the beginning of colloquium asked me, do I know that I'm responsible for the death of his friend? I said, no, I don't know. The situation was like this. His friend was taught that string theory is a theory of the world, and he devoted several years to study string theory, and when it turned out that it is not the theory of the world, he committed suicide.
What do you mean, not theory of the world? Like, can you prove that string theory is not a theory of our
No.
world?
When he got a feeling. So you see, so when the person commits suicide, it's not because he doesn't have a proof, it's because he lost this feeling. So that's why I'll try to describe different things in my introductory lecture. First thing, what is physics? Second thing, what is mathematical physics? Theoretical physics. And third thing, how M theory plays of M theory in this picture. I'll speak a bit about history of science, a bit about history of mathematics, a bit about history of physics, just to give you proper understanding of what these things are all about. So, let me start with mathematics. In mathematics, there was a science called geometry. When people study geometry, geo means earth, metry means measure. So measuring earth is something like physics. It was physics many years ago. But then this geometry became mathematics. Euclid. Probably like this. Euclid made it mathematics. What happens then? Then there was a great discovery of desert. So there are new spaces. projective space. And you may study geometry of projective spaces. You may ask a question. If our space where we live in is projective, the answer would be no. Our space is not projective. What is the reason to study projective space? The reason was it is an interest in mathematics. Mid of 19th century. Lobachevsky geometry. Bolyai geometry. So new geometry. You may ask, if our space has this geometry, the answer would be no. But why do we study it? Mathematicians would say it is interest. It is because our space is included in the family of spaces. Imaginary space. And there are interesting properties of these imaginary spaces. And property of our space is a specification of these universal properties to our space. And that's why it's interesting. However, we live in the practical world. What is the practical application?
So just small comment. So at least current kind of state of cosmology believes that in far future and far past we live in anti-de Sitter space, which is a version of Lobachevsky geometry. So that's why apparently it has a lot to do with our world. So.
Yes, that's what I was trying. But we live. Okay.
So,
yes, that's what I was going to say. In the middle of the 19th century, it was just pure imagination. But then, in the 20th century, it turned out that this pure imagination became general relativity theory. Okay. So that was the fate of geometry. And if you ask what geometers are working on right now, you would see that geometers now are working on various generalizations of the concept of space. They are working on so-called non-commutative spaces, A-infinity spaces, and many other fancy things. And they are proving interesting theorems about it. So in geometry, the main object is the space of spaces. So this is our particular space. These are spaces of 19th century. These are spaces of 20th century. And this is what people are working now. And relations between these spaces. So geometry is not geometry anymore. It is a theory of spaces, and it is useful. Because in order to get general relativity, people just took the development of the geometry from the 19th century and used it in 20th century. Okay? It's a story about geometry. Now, let me go to physics. But it is interesting that before I go to physics, I'll speak about another science. And this science would be, surprisingly, chemistry. What is so interesting about chemistry? So chemistry was something that was developed from, that appeared from alchemistry. So what is alchemy? Just for your culture. Al is the article in Arabian language. And all this started when there was great Arabian civilization in Eurasia. So alchemistry was an art to find one of two things. First thing, process.
Not one of the things, both things. Better both things.
Both.
Both better. So-
Okay. Find process that turns everything into gold.
So typically cheap metal into gold.
Yes. Thank you.
So they kind of didn't try to turn, say, wood into gold. So they had some understanding that it probably should be some metal.
Philosophical. It's something that cures all disease.
Yeah, so it's common kind of desire to be rich and healthy.
Yeah. And you see, they got financial support.
Everybody wants to be rich.
And they promised, you see, and they gave this promise to people that had money. So kings and rich people were financing them. And then they were trying to mix substances to heat them, they pronounce spells over this heating. Unfortunately, as you know, at first sight, they did not succeed. However, there was a kind of revolution in this process that made it chemistry. They were secret notes of unsuccessful attempts. And then at one moment, I don't know who, decided not to throw these notes away. Keep these notes. Our substances move into substance. And these nodes of failed attempts is what we know as chemistry. Keep nodes on successful attempts. And that's what we call chemistry. So now let us see on this process. What did we got out of it? We, instead of philosophical stone, we get biochemistry. So it takes a lot more money, like hundreds of billions of US dollars. And not like several people working together in the lab, but great pharma corporations. And it is not curing all disease, but curing a lot of disease. So I would say that here we have plus money. What about the process number one? People realized what?
No, process number one is complete success. So no. Nowadays we can turn like any metal into gold, but it costs more than the cost of gold. So in principle, we successfully got this one. But economically it's not viable.
So I will write it like this. Moreover, it turns out that it's not so important to turn things into gold. What is more important is to turn things into helium-3 for thermonuclear synthesis.
I'm not sure. Like thermonuclear synthesis,
Okay.
it's still not clear whether it is a thing or just continuous experiment. So,
Okay, so but you see, for me it is a lesson. You see, now let us come to physics. You see, all of these was a pre-story.
I would say like, okay, one comment since you said like helium-3 and thermonuclear synthesis, so I think like nowadays version of one is to find some way, like some catalysis or some way of tunneling under the barrier, under the barrier of electromagnetic repulsion of two protons. So
Yes.
so that's kind of a problem to which people try to find a solution. That kind of stupid way is to just heat your like hydrogen atoms to very high temperature to bypass this barrier. But maybe there is a smart way.
But you see, this is kind of a story, because I want to draw a moral from this story. Okay, so now I'll destroy the. So let me talk about physics. You see, everything that I am explaining today is related. I just want you to keep in mind what I am saying. What is physics? Physics is the extension of geometry. In geometry, we measure Earth. In physics, we study law of nature. So nature is the generalization of Earth. And law is generalization of measure. In this way, physics is a generalization of geometry. So what was discovered? First, it was discovered that experiments go into laws described by mathematical formulas. Second, mathematical formulas may be deduced from mathematical models of the world. So these mathematical models of the world, people call theories. Okay? So what one can expect? That this is a set of experiments. And these are prediction of theories. Say, theory one, not very successful. Theory two, much better. Okay? But theory one, say, gives something like this. Theory two gives something like this. It explains here, but it's not explaining here. And then people were thinking that gradually you will get theory three and so on. The development of theories would bring you something that is closer and closer to experiments. Okay? And it was like this. And if a theory gives you something like, I don't know, like this, you would say the wrong theory. So people were keeping good theories and throwing away bad theories because they believed in this process. So it was just like in alchemistry. If you go closer to gold, you keep it. Okay? If you are definitely getting shit, you just throw this process away. But then, interesting thing happened. And it actually happened in the beginning of the 20th century. So what should I like to keep? Okay. Approximate. Let's see. Kaluza theory of unification. Of gravity and electromagnetism with the help of fifth dimension. Wow. It was so great that Einstein was referring this paper and he was holding it for 2 years. Probably he was jealous that he didn't discover it. So beautiful it was. However, immediately people realized definitely not the theory of our world. So what should we do with it? So physicists in the first half of the last century was thinking what to do with it. They did not put it into books on theoretical physics. In particular, in Landau leaflet, nothing about it. I don't even think that Mr. Thornton Wheeler book on gravity has it. It's already the second. So this Landau, if you heard about such a physicist, he was a tough guy. He said, first of all, why is theory not the theory of our world? Because it predicts that there are particles with integer charge and integer mass. And we don't see it in our world. So Landau asked people, could we save this theory? Could we find the way how to get rid of this set of particles? This set of particles is called Kaluza-Klein tower. And the answer is no. And that's why it was discarded. And it was not included in the course of theoretical physics. Because these days, it was only theoretical physics.
Why the answer is no? Like in principle, making the circle like arbitrarily small, you can make like the mass of the first particle in a tower arbitrarily large.
Yes, but
which is beyond kind of validity.
Because in our world we have electron that is charged and light.
But Okay. The electron should be part of this tau.
Yes, of course. And it was exactly the moment when theoretical physics and mathematical physics started to go away. Because theoretical physics was studying theories that could be theories of our world. And mathematical physics was just studying interesting theories. Like, let me go to this alchemistry example. Suppose you take a metal, you have another substance, and then you get a boom. No gold, but a lot of smoke. Okay? So in chemistry, you keep trace of this process because it's an interesting boom. In alchemistry, we said bullshit. So that's why when people kept keeping Kaluza theory first act of mathematical physics. Like keeping process that definitely does not lead to goal. Now, what happened then? It turned out that it was a wise thing to keep it. So in Kaluza climate, in Kaluza theory, that we will study in this course, of course, the space-time is S1 times R d1. So it is the space-time, and here is S1. That's Kaluza. There was also a Klein field, approximately 1938. So how could you replace S1? The easiest way to replace S1 is to replace it by S2. So if you study the gravity here, gives Young-Mills field. Wow.
Two comments, like, so when Andrei says gravity, it means like pure Einstein gravity.
Yes,
like
gravity and pure Einstein.
Because nowadays, like, gravity is kind of more general concept. So there are like many different gravities. And Young-Mills theory with a particular gauge group, because Young-Mills theory requires specification of gauge group, and
with gauge group, yes, this was exactly the group of isometries of two-dimensional. So would people, you see, there was a Second World War that mixed, you see, so people stopped thinking about pure imaginary worlds and started doing weapons. But as this year, would they think more about it? So Pauli, they could get young Mill's theory 15 years early. Wow. That's why it is good to keep it. And this move from Kaluza to Klein is the first step, the first act of mathematical physics. So to keep Kaluza is the first thing. To go from Kaluza to Kaluza-Klein, probably it's called the second step. First you keep it, then you use it. So how do we understand mathematical physics after this? Approximately in the same way how we understand geometry. Space of fields. Okay. And what we have here? Here we have phenomena. In particular, in some theories, there is a gravity. In some theories, there is no gravity. In some theories, the space is four-dimensional. In some theories, the space is two-dimensional, and so on. So, mathematical physics studies all theories, and our theory conjecturally somewhere. It studies all theories that have potential to be connected to our conjectural theory somehow. So we put conjectural theory of our world in the space of all theories. And we do not need to say that we study theories that could be theories of our world. We study theories that are like theories of our world. Let me try to explain it in the desired model of projective space. Consider RP2. RP2 is a semisphere, and these things are identical. It is not a reality. And it is definitely not our space. However, we include RP2 in geometry because it is in some sense similar to ours. So this is our space. This is why they are similar. Both are two-dimensional measures. In this way, they are similar. However, there are properties that differ them. But we study both of them in John, knowing that this is not ours. In the same way, in mathematical physics, people study the space of theories. Okay? Similar to our theory. Sometimes knowing that theory is not our theory, but similar in some sense. In particular, Kaluza theory is huge. So this is, we don't know yet what is the theory of our world, but Kaluza theory is. Okay? Now, let me briefly explain to you. So, when people study geometry, they do not study all possible spaces. They study spaces that are interesting. How to explain what does it mean to be interesting? It is very hard to give a definition. It is just a feeling that the space has interesting properties, like this RP2. You may feel that this RP2 has an interesting or strange geometry. In particular, in RP2, we have the following. There is a cycle, because these 2 points are identical, that could not be contractible, but if you take it twice, it is contractible. Interesting property. We don't see this property in our book. So this property is called the torsion of the homotopy. So it is interesting. If you take something like 1057 dimensional space, it will be very complicated, but we study interesting properties. So that's what geometry studies. Now let us come to mathematical physics. So that was physics. You see, I distinct physics and mathematical physics. In physics, we had elementary particles. Fermions, like neutron proton, mesons, like pi, rho, etc. Those leptons. So this is physics. It is physics. So what is theoretical physics? Yes. And here I will use very important word. Attempt. To describe physics from standard model Lagrange. It's an attempt. So people are going in with shirts with Lagrangian of standard model. It was popular like 10 years ago, when you were in the kindergarten. But to write down Lagrangian does not mean to describe. It is the first step of description. And people try to describe quantum field theories from Lagrangians, and sometimes they fail. It is because Lagrangian is just recoupling limit of a theory. Limit. Let me go to the space of theory. So there is a concept here called cup. So when we are here, theory could be described with the help of Lagrange. If we are far away, theory probably could not be described by Lagrange. And probably we will also talk about it. It is the program of many people. Maybe I'll talk about it, but not on this course. So you should understand what is physics, what is theoretical physics, and now I'm thinking, okay, I'll go to this. And now there is a good question in the world of theoretical physics. First, how to describe quantum field theory, I would say. I put it like strong up. Or what is QFT? How to introduce gravity? So these are questions. And in order to answer these questions, we need to broaden our scope of research. And it is exactly the place where mathematical physics. So there are several concepts. First concept is the concept of supersymmetry. So supersymmetry is a odd symmetry between bosons and fermions that was not found in our world, like Kaluza-Klein tower. But it has a beauty. And the beauty is that is in some sense studies topology of quantum field theory. And we will talk about it. So this is a concept of mathematical physics, like Kaluza theory, not found in our work at all, but remarkable because of its beauty and potential help. Nobody says that it would help. There is no progress. But it is so interesting and so beautiful and so related to mathematics that there are like 10,000 papers on it. Second, ring theory that belongs to superstring. So the property of string theory is that it contains gravity. And has no ultraviolet divergence. Okay. And what could supersymmetry say? One is promoted to one filter. It is called supergravity. In different dimensions. And among supergravity in different dimensions, there is a maximum. In the equilibrium. I'll explain what does it mean to have maximum. If you have supergravity in some number of dimensions, you might do Kaluza-Klein process to get supergravity in lower number of dimensions with some extra fields. But maximum supergravity is supergravity in 11 dimensions. Superstrings live in the state. So there are two mathematical physics candidates for the most elegant model, not the model of our world, but for the most elegant model, like Kaluza model. There are two candidates. So both models were incomplete, but they were incomplete different. Superstrings were understood only as perturbative theory. Supergravity understood only classical. But there was, of course, hope that supergravity would or should be understood as a quantum theory. And now we are coming to the M theory conjecture. So before I formulate it, I want you to know that these two models, unlike model of Kaluza, model 1 tilde and model 2 are incomplete. Okay, I'll go to this bit. So there is so-called M theory conjecture. Eleven-dimensional supergravity. Compactified on S1 is isomorphic to superstring. Now let me explain why this is actually not like conjecture in mathematics. What?
We're going to make a break.
Yes, and now I'm going to make a break. Thank you, Slava. So I'm sorry for all this philosophy, but later in the course, I would write simple formulas and do computations, and you should know why I'm doing all this, what these computations are all about, why it is interesting. Okay, so let us have, so what is the rule, 5 or 10 minutes break?
Up to you.
Okay, so let us have a 10 minutes break. But of course, before the break, are there any questions? Maybe you have some fast questions, immediate questions. You can ask any question.
So what does the M series M stand?
So magic, mystery.
Or Witten.
So some people say that it is Witten turned around, but actually it was not Witten who invented it. So the main people who played the role in inventing M theory. Yeah, I'll say it on camera. Nobody will let me in the United States. So creators of M theory was Ashok Sen, Chris Hull, and I forgot his name, Thompson. So I will put number 1. They will kill me for this page. So they did it. And then Witten summarized. So it's not because of Witten. So Witten created the name. And there was also Palczynski. He has I here, or Y. I never think it.
I.
Some people call it matrix. So it is a standard name. Oh, I forgot to tell you that M theory is the most ambitious project of humanity in mathematical physics. Most ambitious. You see, as any project, it could fail, but it is the most ambitious. So people were doing it for 30 years. About 100. Oh, I will say more about it after the break. Okay. Now I'll tell you some secrets about M theory that people avoid to say loud. Okay? So actually, people avoid saying something because there was a great financial investment in. Okay, I need to explain it to you. So we need to know what happens and how to read articles. Okay, so I'll spend some time. I said just a bit more about philosophy and history of science, so you would get the picture. Okay? So later today, we will write down 4 books. In 60s, situation in high energy physics was like this. There was mysterious mesons and baryons. The understanding of that writing Lagrangian for mesons but not limits to understanding of physics. Now just compare. Isn't it a little bit like what we have with gravity? Sorry, this is what people did with B. It's called S-matrix problem. So what is S-matrix problem? People say, we have built huge accelerators. In these huge accelerators, we are measuring S matrices. We are not measuring Lagrangians. So now let us study property of S matrix. two particles going in, some particles going out. So we have a pole when energy, the S of one particle and another particle, give the mass of the intermediate particle. Okay. It was S matrix problem. Now, there was so-called duality amplitudes. Because pole could be here, pole also could be in this channel. And that's how people found dual amplitude. Okay. (1969), people found dual. They were called dual resonance. And then they realized that the dual resonance amplitudes were actually coming or could come out of strings. Quark, anti-quark, another quark, anti-quark, and so on. So here we have two mesons, and here we have. And it was a picture, it was a model. By the way, exactly like in Kaluza-Klein theory, spectrum of mesons and amplitudes of mesons were not exactly like predicted by string theory. Just like in Kaluza-Klein, just like in Kaluza model of gravity. Idea was quite interesting, but result did not fit it with experiment. In the year 1973, strings were considered as a dead end. Official end of strings. 5 remaining people form a group. And studied string theory from 1972 to basically 1983. Cool. Blink, quartz, green, microwave, nebulous, and I forgot the Schwarz, Ramon. Maybe there was the sixth one. Now everything is called by their name. But at that moment, they could barely find a job. They were young postdocs. In the year 1974, and there was a Japanese guy who gave this idea that closed string is a derivative. So it was a revolution inside string theory, but it was not accepted by other people. So it was internal string revolution. In the year 1982, 1983, Edward Witten put on his board a task, finally close string theory. And knowing it was one of the problems that he wrote for himself. In the year 1984, people call it string revolution. It means that Princeton accepted strings. So if a theory comes to Princeton, it means that you win. So revolution is not when you have something like you have your camp in the mountains. Okay? The revolution wins when you take the capital. Okay? That's why people call this first string revolution. And one of the slogans of the first string revolution was slogan. Slogan one. String is the only way to put one size bracket. Give money. And people gave money. And people who got money, people who received money were David Gross and Edward. Of course, not in their own pockets. But it was possible to open string theory positions all over the world. From Japan to Spain. Now, interesting. Once again, there was a group of revolutionaries, these guys, Hull, Townsend, Sen, some other people, who were doing things they called black brains. They call themselves small but prominent group of people. They studied black brains. And the idea was that they are doing nonsense. Once again. But you know, when you have revolutionaries, you sometimes have revolution. So they were making this plot in this year. And in 1995, they took a Princeton again. March. It's called Second String Revolution. Paper of the week. So when revolution, so you have a revolution when the king endorses the new government. So Edward Whitton is like a king. When he endorses, it means that you made a revolution. Oh yes, like a pope, yes. Yes, right. Exactly. Okay, now it's interesting to note. Now I'll tell you some secret. That the very conjecture of M theory implies secret. Do not tell to anybody. There is an 11-dimensional supergravity without strings. We will discuss it later on. So the slogan of the first string revolution contradicts with the slogan of the second string revolution. That's why you should not follow slogans. You should just try to understand what is going on. And this is much harder. And that's what we are going to discuss in what would follow. Now, people were so active in the second string revolution that was hidden period, boom, and then you may think, what happens here? Activity went down. And do you know why? Activity went down because nobody managed to guess what is the internal structure of activity. Let me try to explain it to you in some picture. Consider the cylinder.
It is something three-dimensional. And consider the world of two-dimensional people. Okay. And there is the sun. So how will they see the cylinder? Sometimes they would see it as a circle. Sometimes they will see it as a square. But they need to admit that this is equivalent to this. Only by imagining the third dimension, they could understand that circle and the square are the same. So it's hard to imagine. So when I say something about M theory, because we know, what do we know? Plenty of evidence that M conjecture and in several classes you will be able to get the first confirmation. So there is no doubt that it exists. We know properties. And some rules how to manipulate. We do not have mathematical definition. So in some sense, all this is parallel So in 1950, when Feynman defined functional integral, it was a little bit like this. It was a symbol that had no mathematical meaning. Okay? No rigorous mathematical meaning. We understood it only in some particular cases. We have plenty of evidence that it worked. We knew some properties and how to manipulate, and we did not have mathematical definition. So, do you know what young people often think? In old times, 20 years ago, 40 years ago, 60 years ago, the life was so interesting. People were that great. They were solving real problems. And now, some problems are solved, and some problems are too hard. So there is nothing for me. So I know it because I was young. Okay. So it is a problem. It is a problem. So problem of 50s was to understand functional integral. Problem of 95 is to understand M theory. And if we understand M theory, probably, but not necessarily, only probably, we would understand something about quantum gravity. I do not promise if somebody would study M theory, devote his life to M theory, and then commit suicide, it will not be on my hands. Okay? But once again, this concept of M theory is the most complicated, most deep issue in mathematical physics ever. At the same time, you may study other things, right? Still there's a question. What is QRT? And I want to say that these two questions are different. Main questions are, what is QRT? What is that? What is quantum gravity? And what are relations between them? If you don't like something, you may skip the course. So now I have a feeling that I left some time for questions. Yes? Please ask any questions. So could you say it louder, please? On the F theory. F theory is not really a theory. What I mean by M theory includes F theory. Because M theory is a concept. It's not just 11-dimensional supergravity. It's 11-dimensional supergravity together with the conjecture that 11-dimensional supergravity units one. It is a pair. And when people are talking about string theory, they mostly mean M theory nowadays. So some people say a theory that was called M string theory. So I actually want to give an introductory course. So people who would enter this course would be able to understand something that other people explain. Like understand something that happens on seminars. You do not need to work in M theory, but you need to understand something about it. Okay? So that's why I will give an introductory course. As it should be as easy as possible. And also I will give a class. So Slava, what is the time?
Yes, so there will be another lecture today at 2:50 p.m.
No, so I want to shift it by 35 minutes.
Later or earlier?
Later.
35 minutes. Okay, so that means 3:25 p.m. How will you today?
No, for 3:30. Тим, 3:30 нормально? 3:40?
Knot theory now ends at 240.
Okay, at 340. At 345. Sorry, I forgot the next class. Three 45. I'm sorry. It's for the rest. But I decided not to go to administration to shift.
No, but we eventually need to change the schedule on the website.
Yes, 345. And this would be very elementary. So, any other questions?
Since you drew the comparison between the this M theory program and the functional integral program, what would you consider like some outcomes and results of this program of the 1950s? What would you consider as like success, or what's the
Okay.
So like a similarly stated program, what were the results in your opinion?
Okay, so let me give you my understanding. That now, 70 years later, we have so-called functorial. Oh, sorry. So that's what we have now. Functorial definition of Q of t. It includes non-perturbative C of t of 1984 by Belavin. Polyakov. So it was 1984. So in 25 years, we got non-perturbative quantum field theory in dimension 2. And now we get more and more understanding of what is quantum field theory. Like functorial. There are other attempts. What is interesting is that in functorial definition and already non-perturbative CFT, Lagrangian is often eliminated. No Lagrangian. So we are starting to see how to define the functional integral, and the outcome is that there is no Lagrangian. So there is a revolutionary concept. And there are so-so concepts. When you are trying to understand some object, sometimes it means that you need to change the initial problem. And here we see this, what is M theory? Maybe we need to change the initial setup. And if you ask me how to change the initial setup, I would tell you, if I knew how to change the initial setup, I would talk about it in Princeton. But you see, it is the obligation, it's the duty of all generation. All generation brings questions, young generation gives answers. I am carrying history. I am carrying questions. I am showing relations.
Yeah, maybe one small comment which is kind of related to the second part of your course. So like in recent years, like the progress about understanding of, okay, not M theory, but properties of M2, say M2 and M5 brain is related to kind of concept of ADS-CFT, which you did not include in kind of major things related to M theory and progress of modern theoretical physics. And that's, by your terminology, is also like accepted in Princeton, and we
Yes.
wrote a paper on it, and that's a big thing. And Tomoki, I presume, will talk a lot about it in the second half of the course.
Okay, let me tell you something. That there is also ADS-CFT conjecture that is like this conjecture. If you accept this conjecture, you also get many checks. And these checks go. So I don't know. So from my point of view, ADS-CFT is an extra conjecture. But of course, it's a very important conjecture. And you may say, if you do not use ADS-CFT, you have this and that. If you use ADS-CFT conjecture, you probably get more confirmation. So ADS-CFT here is just an extra property of this unknown 11-dimensional supergravity or other supergravity. So actually, ADS-CFT we won in Princeton in 1998, I think. There was a string conference, and people were a bit drunk. And they were dancing, and they were singing Hey Maldacena on the motive of the song Hey Macarena. So there was a popular song Macarena. So instead of Macarena, they were singing Hey Maldacena. And from here, we have this ADS CFT that's also conjecture. And what is important about this conjecture is that it's very hard to prove it. You cannot prove it because you don't. Okay, it's important thing. In mathematics, if you have two setups, you have a conjecture that the left-hand side equals to the right-hand side. So you cannot prove it in general, but you can prove at particular cases. But what if the left-hand side is not rigorously defined? So you can only check that some property of the left-hand side coincide with the property of the right-hand side. And that's why no mathematicians are working in this area, because they cannot work with something that has no definition. Okay. And ADS-CFT is basically the same concept. So once again, it is the hardest problem in mathematical physics ever. You see, I know that the problem to construct a rocket that goes to Mars is very hard engineering problem. The problem to, I don't know, to cure cancer is very hard medical problem. Okay, the problem to construct thermonuclear reactor that works is also very hard problem. But the hardest problem in mathematical physics is to understand what is going on. Something is definitely going on. We just don't understand what is going on. And as a result, so how do we know that the things are working? It's because that from this M theory, you may deduce many mathematical conjectures that turned out to be right. You see, you could not have an empty thing from which you can get non-trivial mathematical conjectures. So it is indications that this thing exists in some sense. And that's why people are still working on it. Okay. Okay, so I hope that I have finished with philosophy. There will be no more philosophy in the course. Okay. No more philosophy, no more history. Just a little bit. Okay. So let us come to the first essential lecture. Once again, don't be afraid. It will be very elementary. So as a physicist, I came from high energy field. So my historical reminiscences are all about high energy fields. And now let me imagine, for analogy, high energy theory of 60. So I was just born at that moment. However, I understand what people were talking about these days. There was a big accelerator, and there were mesons, and there were also bearings. And people were trying to understand some order in this business. And what did they measure? An experiment. They measure charge. At that moment, they measure electrical. They measure mass. And later on, they measure so-called SU2 representation. And they call this SU2 representation isospin. This was called isotopical spin. So what did they found? They found that it is good to consider mesons as made out of quark and antiquark. And they found that baryons are made out of 3 quarks. And these quarks could be up or down. And this SU2 was just acting here. And they told us, we don't know why baryon is made out of 3 quarks, but we assume it. We don't really know why meson is made out of quark and antiquark. We assume it. We don't know why we cannot see the 3 quark. Later, people called it confinement. But at 60s, there was no idea why we cannot see the free quark. However, there is a rule. Rule was like this. And masses were approximately the same. In particular, photon was U, U, D. So here we have 2/3, here we have 2/3, here we have minus 1/3, and neutron was UDD. And charges was plus 2/3, minus 1/3, minus 1/3. Totally here there was plus 1, totally here we have had 0, and it was exactly that we measure in experiment. Proton with a charge plus 1 and neutron with a charge 0. And people said, wow, that's great. Then strange particles appeared. So quarks were up, down, and also strange. And strange quark was heavier. And there were also some interesting mesons, like US bar, meson like this. And this meson was called K meson, actually K plus. And mass of this meson was heavier than the mass of, say, U D bar, that was pipeline. And difference was the difference between masses of quarks. So that's how it was done in 60s, without any deep theory about quark interactions. Deep theory appeared later. Okay? So I'm going to explain M theory at the same level. Like in the case of quarks, we do not have a complete theory. Moreover, to tell the truth, right now, we still don't know how to compute the piece of the mass of the meson that is not related with the fact that M of the strange quark is bigger than mass of the U quark. There is a huge piece of the mass inside this interaction. We still don't know how to compute it. 60 years after that. But still we can say something. And in the same way, I'm going to say something. So now I am leaving our real world and going to mathematical physics world. Okay? What can we have in a general mathematical physics field? Point number 1, we have gravity. Point number 2, we have particles. Point number 3, we have field. And point number 4 is something that people do not know sometimes. We have brains. Let me explain the concept of brains. Brains is an abbreviation from membrane. So what is membrane? It is something like this. So it is membrane that makes it down. This is a spring at this time. And this is a pump. People wanted to unify all these objects. How to unify it? they decided to cancel this map and call it P braid. For particle, P equals to 0. For string, P equals to 1. And for membrane that start all these naming rules, P equals to. Interestingly enough, the trajectories of particles is one dimension. Trajectory of string is two dimensional. Trajectory of membrane is three dimensional. That's why at some moment people invented very strange object called -1 brain. So what -1 brain could be?
Not people, British scientists. So that's a purely attribute of British scientists.
Yes. So it happens because when people were doing this brain business, it were British scientists who gave these names. So instead of the dimension in the space-time, they gave dimension in space. So, and since nobody paid attention to them, nobody corrected them in how to call things. And that's why if you want to have something that happens at an instance in the space-time, it is called -1 brain. So it's very inconvenient, but it is a standard notation. Okay, extended object. Now let me assume that you know classical physics and a little bit of quantum field theory. In the classical physics, you know that there is such a thing as an action. So I will write you classical motion of all these guys. So X is the action of gravity. Okay, I can even write it down. R of G, square root of G. So it's the Einstein action. Plus what you can write for a particle. For a particle, you are writing this, mass times the length of the trajectory. So I am working in the coordinate system when the speed of light equals to 1. Interestingly enough, I can generalize it to brains. So this is for 0. And here immediately you see, so how to generalize it to string? So what string has, like particle has? Area. I call it A. And now, what power of mass should I put here?
Second.
Yes, you need to put here second power of mass. And this thing is called tension.
Yeah, but then you need like some power of mass in front of the first term.
Ah, you're right.
Like if you keep in track of mass powers, so
Okay, then what type of dimension should I put here? I should put here dimension that is, so I'm working in capital D. Capital D is space-time dimension. I think it should be D minus 2. So here I put tension. Plus, it's easy to see that for a P brane, I need to put m to the power p plus 1 and here volume of the brane. I call it BPR brane. Okay. So when I say m squared, it's better to call it tension, not m squared. It's better to call it tension. So this mass, now we understand that mass is tension 0. Here we have tension 1. And here we have tension P. So dimensionality of tension P is m to the p plus.
Yes, so we need to erase p plus 1 power.
Yes, thank you. Okay.
So there
At
is
the moment,
one small subtlety, like even for a particle, so in nature, we have kind of not only scalar particles, but we also have spinning particles, like particles with a spin.
I'm sorry. Maybe something happens, maybe.
Yeah, so in nature, like we not only have scalar particles, but we have particles with a spin, like electron. So electron is an example of particle with a spin. So there is a way to kind of modify and introduce a notion of spinning particle. But like for brains, do we have a similar story? Do we have in some sense like
Of course, we have spinning particles, we have spinning strings, but these are details that I would like to avoid. You see?
okay.
You see, here's my picture with accelerator.
Yeah, but quark is precisely an example of non-scalar particle.
Yes, quark is example of non-scalar particle, but in my example, I have a professor who is teaching guys that are going to build an accelerator.
Okay.
So most of their job would be to build an accelerator. And then professor tells them something why they are doing all this stuff. Okay? And it is called introduction. It's called, you see, this is elementary particle theory for experimentalists. Okay? And in the same way, I am not going to teach you detailed course in M theory. I am going to give you some impression of M theory, so you would know what it is all about. And if you'd like to go into detail, we can go into detail. But I am sure that only 2 or 3 of you would like to go into details. But all of you should know what it's all about. Okay?
Oh, sorry,
Yes.
why different dimension of volumes can exist simultaneously? Why sometimes L, A, and
Because sometimes you have a line. If you have a line, it has length. If you have a surface, it has area. The area of a surface is measured in square meters.
So why do we take summation of all of them?
It is because from this point of view, and it is something that was not clear many years ago. we have everything in our world. We have in our mathematical world, we will have everything: particles, strings, films, and so on. In particular, imagine our real world. In our real world, you have something that is like a particle, but you can take a ribbon. It's not fundamental, but it is like a string. And you can have a film, like a trampoline. Of course, all these objects are not fundamental. But when I'm talking about these elementary particles, I am not talking about what is fundamental and what is composite. I'm just talking at the level of accelerator physicist. Accelerator physicist knows what kind of particles you will see in experiment. Okay, mathematical experimental physicist would know that in his mathematical world, there would be extended objects of different dimensionality. Just assume it. Just try to imagine. It's not written in the textbooks, but just take it and try to live with it. That such objects happen. You may say, okay, they are made out of atoms, okay? You may ask how it could happen on the fundamental level. Okay, good question. On the fundamental level, they could happen as following. Suppose you have a system. So this is V equals 2. And suppose the system has two vacuum. Okay, so it's a scalar field with this potential. So on the left, you can have left minima, on the right, you can have right minima. And here you will have some interface. And on this model, this interface is a line. So sorry, and plus we have time. So D equals 3 to space-time dimensional time. And here we have the line as an interface. You may consider it as a string. And if D equals 4, it will be a surface. This surface was known as a domain wall. And if you have a quantum field theory, you need to say that at your quantum field theory, you have not only particles, but also domain walls. And domain walls have this dimensionality. So people observe this, that this could happen in quantum field theory. But you see, now I'm explaining things at the level of experimentalists. What could we measure? We could measure all these guys, and this is how they are coupled to gravity. At the moment, I have not spoke about fields. Okay? Plus, there is an action that is depending on fields. In my oversimplified presentation, I will say that my fields would be K forms, omega K. Okay, I will call them small omega. Omega K means it's a K form. Now I need to write down the action for these K forms. So how will I do it. I would like to do it in a universal manner. I will write omega k, d omega k, star d omega k. And this is the Hodge star. And this Hodge star depends on the metric G. If you don't know what the Hodge star is, let me give you a hint. You see, I want to be elementary, and I would be elementary. D omega k star d omega k is. So omega has k indices. E I1, I2, Ik plus 1. DJ1 omega J2 JK plus. So I have indices I1, Ik plus 1 down, G1, GK plus 1 down. Then I take metric. And then I take square root of the terminal of geometry. So this is for physicists.
You might also need to anti-symmetrize in I1, Ik plus 1.
So physicists understand in this on this level. Mathematicians understand on this level. So take your side and understand. In particular, in my talk, I would always give example. So what happens when k equals to 1, to 0? D omega 0 starts d omega 0 integral is just dI omega 0 dg omega 0 g by d. And this is called scalar. For k equals to 1, okay, I will not write the component then. Here. Omega 1. K. 1 4. Roughly speaking, connect. So if we have a 1 4, then the action written like this is a Maxwell action. And this it is invariant under the shifts a going plus to a plus d epsilon. Since d squared equals to d. Okay, so people should know it from classical field theory. Now, this action is also invariant under the analog of the gauge transformation. Omega k goes to omega k plus d epsilon k minus 1. So this is higher generalization gauge symmetry. And it would play a role later. Okay, here I said something about particles, about masses, but I have not explained what happens with electrical charge. K brains. Sorry. This English notation. K plus 1 brains may be coupled to K4. And here we have a charge coefficient. We know this from electrodynamics. This happens for K equals to 1.
So it's
K minus 1.
minus.
So particles could be coupled to 1. That we know. We also know, similarly, we can study the coupling of the string to the two form. These two forms sometimes is known for the string as a Kalb-Bromley form. And similarly, three-braid, I call it QM, would be coupled to the three. Okay, so this is how masses and charges and everything match. Now, interesting statement. And the statement is, what about gauge symmetry? What happens if omega k goes to omega k plus b epsilon k plus 1, k minus 1? We know what happens in electrodynamics. If trajectory is closed, we have invariance. If trajectory is open, it is a boundary contribution. Similarly, the same phenomena happen for brains in higher dimensions. So my goal now is to show you that on this level of mathematical engineers, brains are not very frightening. It is just a very natural generalization of a concept of a particle and string, if you heard about strings. If you never heard about strings, probably you heard about particles. Okay. So nobody asked me a good question. And I'm looking for this good question.
there are
Yes.
no canonical. Okay.
But there is this good question.
So I have a question, like, everything, all the actions that you wrote, they all depend on the metric, including the length and the areas. So
Yeah,
are they
it's
supposed
a
to be-
coupling to
Yeah,
gravity.
yeah, so it's supposed to be under the integral for the metric, right? Kind of.
Yes, but we know what length is. Length depends on metric.
Yeah, yeah,
Length of G. Area depending on G.
So I have a question. There are no canonical way to interpret Karl-Bremen form as some connection, some bundle, and so we can't generalize Young-Mills theory.
It's not a connection, and people are still arguing how to treat it. But it's definitely not a connection. People say something about higher connection, but it's not a connection in the standard sense. Or people are speaking about higher gauge theory. But there was a simple question, nobody asked me this question.
Is there a term that the brain interact with brain? Yeah.
Okay, so at this moment, I have, so it's also a good point about brain with brain interacting. And it would appear if I allow some interesting configurations. If I say that I allow configuration like this, let it be K brain, let it be one brain. If I allow such configuration, it will give me brain and brain interactions. But
No, I think there is another configuration which is like brains inside of other brains. You can imagine this one-dimensional trajectory inside of two-dimensional plane.
yes, but yes. So I would like to say that you can imagine many things.
Yeah, but that would be like coupling of one brain to a two brain.
Yes, you can. You see, now we are going into imagination, and we will study this. One brain inside another brain. So coupled objects, like before we were talking about meson, Q bar. They are basically coupled. And we say that this is a single particle called a meson. Quark could not go away. So you may imagine that in the same sense, two brains are coupled, or one brain of lower dimension is coupled to the brain of a higher dimension. But my question was much simpler. My simpler question was, nobody asked me about what is coupled to the scalar field phi.
Just scalar field related to the point. No.
Yes, yes. Okay, so I wrote it. So Slava, you know, of course you know.
That's why I didn't.
Yes, but it was a question for students. So there is minus one brain. It is a point in the space-time. So scalar field could be evaluated at this point. And then, if I would study integral over position of this point, I will get such a term. And this term may be considered as an extra term
that I am adding to the Lagrangian for the scalar field. Okay. So you may think about it a bit later. So do we have equations right now on this very elementary level? Yes.
Just my question, are the brains open or so if you're considering particles, maybe you can always imagine particles just extending the time matrix from minus infinity to infinity, but if you have the extended objects.
Yes. So when we have you're absolutely right. When we have extended objects, we can imagine the space-time boundary. So for one brain, brains are also known as strings. You may consider, so this is time, one brains that have no boundary, but you may also consider one brains that have boundary. And if we have boundary, okay, I'm sorry. And if we have boundary, we have something like boundary condition. In the year 1970, people were imagining strings, actually open strings. In 60, people were imagining strings as fluxes of chromodynamic shift. They had the following picture in mind. You have a quark. You have an electron. They are charged with respect to chromodynamics. You don't even need to know what chromodynamics is, but you may imagine lines of this chromodynamic force. And you may imagine that when you take quark and antiquark away from each other, then the energy of this configuration grows. Because energy is inside this chromodynamic string. And when it grows substantially enough, it is energetically favorable to break this string here, to create a new pair of quarks and to shrink. And that's how we see confinement.
Have you explained what confinement is?
So confinement is an experimental phenomenon. And this experimental phenomenon in real physics, not in mathematical physics. But we are taking images from real physics and from model of real physics into this imaginary world. So confinement is the following phenomenon. We do not see quarks of charge plus 2/3. We do not see particles that have charges 1/3 of charge of electron and 2/3 of charge of electron in our experiment. All particles, as we see,
have charges 0, 1, 2, 3, or -1. So the question was, how did it happen that we can never see the free quark? And there was an explanation. Suppose we have this, it was called chromodynamic string. And suppose we hit this, let me hit this, trying to take it away. What happens? We have enough of energy, no problem. We can put a lot of energy here. So it starts flying. It starts flying. And here we see the stretching of the string, of the chromodynamic string. And the energy of this configuration becomes larger and larger. But we put here a lot of energy. We really need to see this free quark. What happens? At some moment, energy of the string becomes bigger than 2 masses of quarks. And it is much more favorable to break the string here into 2 pieces. So we need to take energy to create quark and antiquark. But if we do it, we can shrink this log string. And we will not see a free quark.
We will see just meson flying
Yes.
away.
So you take a meson, you take a hammer, you hit meson with a hammer, or with some super crazy supercharged particle. What you see here, 2 mesons, 3 mesons, only mesons, no quarks.
So, why do we assume there is quark? As quark cannot be divided freely, why do we need to assume there exist real quarks? It's not just a theoretical invention.
Okay, so this, you see, this picture is real physics. Is some approximation to real physics.
But yeah, by real, you probably need to add low energy physics, like
Okay, by real physics, I mean physics of our world. And I will always distinguish physics of our world, approximations to physics of our world, and the imaginary constructions that I will talk about. So, such that no one would commit suicide. Okay, anymore, no, it's enough. Okay, so in real life, it is not what actually happens. It's a model. It's kind of approximation to what we think happens. That when we put 2 quarks at some distance, some field configuration appears, and this field configuration has energy that grows when quarks go far away. So how do I know this? How do I know this? So we see it in experiment, and there are also some numerical simulations that confirm this. So it's, I would say, conjectural procedure. I explained this in order to answer the question, what I would have in my imaginary world. In my imaginary world, quark and antiquark boundary of chromostrings.
So this is an example. And that's how people thought about strings in this year. About 50 years ago. And that's why they got some financial support. Because you may just think, what happens if you have this model? If you have a string, you can get its excitation, because a string can have oscillatory motion, it could have rotational motion, and you can look at these excitations and you can compare it with the results of experiment. So it was physics. It didn't work well. Something was so-so, and something was over. So string was a so-so model of methods. So actual revolution happened in this year. When people decided that strings would not be chromostrings, but fundamental objects. Okay. So in this sense, quark and anti-quark are boundaries of chromostrings. But in my mathematical work that I free to consider, or in many mathematical worlds, I may choose boundary conditions as I wish. So one of the type of boundary conditions is that boundary are attached to some submanifold. And if boundary are attached to some submanifolds, these things, these branes, these boundary conditions for strings are called branes. So first of all, it's clear why they are branes, they are surface. There is submanifold. Now why D? Who is D? Yes, D is Dirichlet. Because it's a boundary condition that x of 0 equals 0. It is a Dirichlet boundary condition. Okay, so now we are doing phenomenology. It's an introduction. I really don't want to frighten you. I want to show you that this is understandable, even if you don't spend a lot of time. Okay, now I am afraid we need to make a break. Yes. So, but before break, there should be questions. Isn't it elementary? So what frightens you here? Don't be afraid. You'll be afraid later. Good question. For example, fundamental objects in M theory, nobody knows. Okay, but they couldn't be fundamental simultaneous. So honest answer that nobody knows. So I'll give you an honest answer. So nobody knows what are the fundamental objects in MC. It's first answer. Second answer. Nobody knows if the equation of fundamental object has meaning. I am telling you the truth, because in the high energy theory, physics, where I came from, okay, people were talking about fundamental particles like quarks and composite particles like bosons or baryons. Okay, so people thought it made sense. Nowadays, people treat, I tell you the truth, but truth is longer than you expect. Nowadays, in quantum field theory, people are treating quantum field theory without the concept of the fundamental field. Moreover, in quantum field theories, there are interesting phenomena that is called duality that replaces one fundamental field by another fundamental field, while theories are equivalent. So you see, I graduated from the chair of fundamental interaction in Moscow. But I need to admit that from the modern point of view on quantum field theory, most probably the very concept of fundamental structure and fundamental field is a misconcept. And you will see it in this course as the simplest example. So this is a deep question in physics, you see. Just 2 days ago, I was watching the video. 2 Russian scientists were talking, one philosopher and one that was working in Los Alamos. And the person who was working at Los Alamos said that the philosophical level of the top physicists goes down. They are not able to formulate and answer the deepest question that could be answered. So what fundamental means? So actually you will see, interestingly, that string theory is not about strings. String theory seems to be a theory that contains strings, but there are many theories that contain strings.
How can we describe the dynamics of quantum field?
So M theory is a theory that conjecturally exists and whose classical limit is 11-dimensional supergravity. And that has the same symmetries as 11-dimensional supergravity. But it's only one piece. Second piece is that this prolongation of 11-dimensional supergravity should be such that I will write it several times. Support 11 over S1 is 3 in R10. Yes, isomorph.
What about the dynamics of quantum nature?
Sorry?
So what about the dynamics of anti-real quantum level?
We don't know. I'm telling you the truth. I'm telling you the truth. We don't know. We can get some information from this conjectural isomorph. You see, if you don't lie, nobody would commit suicide. Then we will come to the question, what dynamic means. So when people were coming from classical theory to quantum theory, they found that the concept of dynamic has to be changed. So we know it. Now, we need to come to philosophy. What kind of dynamic? So what is dynamic? what is fundamental field? What is, so is fundamental field something that isn't a functional integral? So these are deep questions. And if fundamental field is something that is a functional integral, then it's not universal constant. And we will see it in these lectures. Probably not today, but in next lecture. It's an important piece. It's called duality. Simplest duality. So when Nikita Nekrasov, my friend and a well-known scientist, was given an interview at IHES, he said that the question of what is M theory and what is quantum field theory is just like question of what is God and what is the meaning of life. So we are thinking about them all the time, and we can only get closer and closer to an answer. And I would think that answer will be surprising, because people spend 30 years not getting a satisfactory answer. But this is a philosophical problem. It's not just a problem to prove, to say, Fermat theory. It is a question of physics or mathematical physics. What does it mean? Nobody knows. And we would like to know. And would we understand this? And would we be able to formulate this consistently? It would probably move us closer to the question what gravity is. So this is just an exercise towards the way in construction of the theory of gravity. And the fact that humanity spent 30 years not being able to solve this exercise. So what? Who told us that God would always give us easy problems? There are problems for 300 years, and each generation would improve understanding a bit and a bit, and our descendants would finally understand. You see? Nobody knows the complexity of the problem, but 30 years, definitely best scientists. Edward Wheaton gave up. It's your turn. All these people who made second, so-called second string revolution gave up. It's true. Okay, so now it's a good time for a break. So let me see the time. We will continue in 10 minutes. So the break should always be 10 minutes.
这边楼下应该是跟我们一栋楼的对比，你家就是咖啡池都有。也是，你会有咖啡机吗？ What we were out like. The police is the folks on the web. Then from so we need to challenge. So something with it. Yes, so we need to do just one is you like what web you are creating Yeah, so they should keep people from seeing us from our website. Yeah, so that's why we need to report. Put on the internet, because if somebody decides to go, we are thinking. What is things? We felt kind of a move of yesterday, yes. Yeah. Because so for specialists, it was colonial, so. But for students who heard something about it, they would open, see, and think, oh, I don't know it. But there are interesting words, constructions, graphs, infinity, graphs like this, coloring. And here we get this. That's right. No. So I think it's important, but student is, I think that's the biggest. That's one is, it's more creative. I don't know they are standard, I'm missing. Who are going is the one that is on. Some of them too much time. Yeah, it's really unfortunately to fix the rest of my pieces during the week of vacation. But it's okay. But it's not this. This can be so we should very object actually learn how it's school, not just rush. So maybe next year it's giving. Yeah, now it's go for this. I mean, maybe this will be some workshop, for example, with local people. That's okay. That's easy to organize with local people from lucky people from Egypt, with Russia. Not and then next year we can try to organize so he that was sitting here, he used to go to schools and yes, and he said that so it's better to talk to him. Oh, yeah. And he said, he tells me what attracts you. Yeah. Okay.
It goes to internet. Even once we change name, we have a good site for it. Just, no, so that kind of compound what students get registered for conference. Yeah, so and it was like very short project as we advertised few days before the month. We advertised well month actually, but I think this each out very decent. I mean, mostly very much where. Many we changed the put it on the website well in advance. Or we can ask one from the time on ICT. We get an inspiration. No, I think that's true, but that's key. I think it's probably most something. It's kind of harder if you want to kind of see what the project is for direction, but we want to also have some kind of research projects. It brings to possible with like longer school, we should have so this school can try to this now. No, but by next winter, I think there will be some qualification. Yeah, I think. Yeah, okay, but the thing is, in some ways, which is in the undergraduate field, that's a very easy time. And that's it. That's right. Unless we wait. Then salary is. That is a way to. It leads to July.可以，它会有一个线，12名，
说到从可以看过一个点的轨迹是这个，这个伽马就是一个点，而且突破轨迹可以看过这个相应轨迹。什么可以看过一个？对啊，所以什么可以用？对啊，其他没有就是一个零后，就他把这种东西叫注意一个 brain 的 trajectory，就是一个点，包括一些点。
Yeah, there is another eraser, so maybe you want to switch.
I would say money or things. You bought it.
No problem.
Okay. Okay, so I will continue. So I want to be very simple. Let us leave gravity. No, we will not leave gravity aside. Suppose we live in the space RD. And then we want to go from the space RD to S1 times R d minus 1. And suppose we have, and suppose here is time. So time direction is at this one. So this is a space dimension. So I'm coming to this issue of compactification. So it is Kaluza. And suppose that radius of this S1 is rho. Suppose we have a big ray in d-dimensional field. Now we would like to look at e-1 dimension. What kind of brains we get? I am very bad in drawing, but just imagining. Right. So first of all, there is a big ray that is a point in this circle. If it's a string, it lies like this. If it's a point, it lies like this. So P brains go to P brain with the same tension. Now, imagine that this thing that was expected to be, in this example, a string, wraps around one. So if it is a string, it becomes a particle. Wrapping once. P brain goes to P minus 1. So what would be the new tension of the P minus 1? T P minus 1. I put tilde because it's P minus 1 brain that came from the P brain. Is
P times something like 2 pi rho.
okay, for me, I don't care about. Yes, exactly. P is not wrong. Okay. Then let me ask another question. Are there other P minus 1 brains that would appear in this configuration? You see, now I'm asking you simple questions. I want you to involve in thinking about M theory.
And this string intersect itself,
Yes, why not?
so it can wrap more than once.
Yes, very good. It could wrap twice. So, with subscript n, that is n, pp, rho. Oh, very simple. Like string that wrapped many times is a particle, and the mass of this particle is the tension of a string times rho times number of wrappings. Good. Now we know that when we have P brain, we have omega P plus 1 folds. So we may not have them, but let us assume that whenever we have, it's assumption, that whenever we have a P brain, it is always charged under some omega field. I'd like to say it is very strong assumption. It could be charged, it could be neutral. In particular, particle would be neutral particle. But let us assume that these forms, that these P brains are charged under these P plus 1 forms. So we have this action in V domain. Now we want to do this compactification. So what can I do? I can take omega p plus 1 and decompose it with the Fourier modes along this circle. And I would like to plug it here. What should I get? So let us start with the simplest possible case. Simplest possible case is where p is -1. It's not very interesting, but we need to get the feeling. What would we get? In this case, it is d phi target phi integral over s1 times r d minus 1. It would be d phi naught, d phi naught. Okay, so if I want sigma to go from 0 to 2 pi, I need to put rho here.
Are you sure that rho in denominator? Yeah.
Rho has dimension of length. K is an integer. So what do I have here? I have the theory of the same type, plus I have this term. And this corresponds to so-called massive scalar field. And this massive scalar field would be quantized. And have quanta that are particles. Of mass K over rho. Modulo. And this is called Kaluza-Klein tau. Oh, sorry, Kaluza tau. Okay. So due to the identification
between fields and particles in quantum field theory. I can think about this as massive fields, or I may say that I have particles. Okay? Now let's go further. I will not go do the most complicated example. Let me consider the gauge field. AI. In the dimension. From the point of view of d minus 1 dimension, AI is AI. I is less or equal to d minus 1. So this is a gauge field. That's a gauge field, we will see. But it also has a d component. It is a scalar. And now, what is interesting is that all of them would have this extra subscript k. So here we will have a scalar field that is massive with the mass again k over rho modulo epsilon. And what you will have here, it's interesting, but you might check that here we will get massive vector fields. So let me leave it. So for k not equals to 0. And for a I 0, this would be gauge. Because they will have no mass. So you may kind of check. Now, let me consider omega that is a two-fold. It has indices ij in dimension B. Because now I will get a new phenomenon. With indices ij would bring omega 2 with the indices ij with ij both less than d minus 1 plus omega I d 2. So what is it? So this is a two-fold in d minus 1. This is a one-fold in d minus
Now the question is, what about this? Would it be a scalar? Kim, would it be a scalar? No, it would be zero because omega is intercept. So this was a question that was checking if you are following. Bourbaki type question, you know? So now, what happens with the couple? And here I have an integral over what? Omega I j. And here I have three. So it is a coupling between the two form. And the worldsheet. So now sigma is gamma times S1. Simplest case, single rectangle. Then I can decompose it as an integral over gamma. And integral over S1. And here I'm integrating the zero part. And this integral is 1. And I see that the wrapped string is charged under omega IB. Once wrap string is charged under omega IB with the charge 1. And what would happen if the string wraps many times? If the string wraps many times, then this factor would give me M, KL. If the string wraps L times, then L wrapped string is charged under omega IB with the charge L. So what do we have? We did the first computation in M3. When we compactify over a set, we got that string creates particles with mass T string over rho, and here we have some L. We would like to write it like this. So this is mass,
Epsilon 12.
and charge L. And we see that for these particles that are charged particles, mass is directly proportional to charge. And this is called Kaluza-Klein phenomenon. And of course, you may ask, why I call it, Kaluza phenomenon. Why I call it Kaluza phenomenon? Kaluza never studied strings. It's true. Kaluza found this phenomena in another setting. When you compactify gravity on a slot. But I promised you that right now we are going to study the simplest things. I don't want to frighten you. And we will come to Kaluza phenomenon and the coupling with gravity next time. And I have a feeling that my time for today is over, and I have not frightened you. At least I hope I didn't frighten you. Now questions, any question?
So here, the mass and the charge are unrelated. Then these numbers, here's the wrapping number, there it was the number of the harmonic.
Okay. Good question. Here we also have harmonic number.
Yeah.
Here we have particles that are quanta of the scalar field with the same law. It is K over rho. Oh, I think I wrote. Yes, I made a terrible mistake. This integral is wrong. I'm very sorry. It's unforgivable mistake. Here rho stands here. Here rho stands downstairs.
Yeah, so more general string configuration would be string which is both winding and has angular momentum in that direction.
Yes.
So then the mass will be like linear combination of these two.
But I will not go to talk about general stuff. I would like to talk about typical example. So this consideration was classical, while this consideration was quantum. If we try to restore H bar, we will see here in the energy, in the mass, no H bar. It's a classical consideration. You can do this consideration if you have a ribbon and you have a cylinder. You put a ribbon over a cylinder and you will have something that would have mass proportional to the radius of the cylinder. It's a classical consideration. There is nothing quantum in it. However, here we have H bar. Because to tell the truth, 1 over R is just a wave vector, not an energy. To make it an energy, we need to put H bar. And what is interesting is that in all this compactification business, there is some kind of duality that would mix them. And still we need to see the following. It is clear how these wrapped strings, particles coming from wrapped strings, were charged. And what is charging these? It's not known yet. We will discuss it next time. In particular, Slava did an exercise on this when he was a first-year bachelor student. Right? You don't even remember. Questions? What are you frightened of?
So here we omit some coefficient. It's integral over some paths, some trajectory of omega ID.
Yes.
So because we don't know up to now, we don't know omega ID explicitly. What is omega ID and what is the coefficients?
Okay, so we have omega ID that depends on X, and let us consider it to be independent on sigma, to be independent on the last coordinate. So sigma is what I call XD. So we have omega ID dxi dxd. So I used to call it sigma. And we integrate it over gamma over the image of gamma times S1. Then I decompose it. The image of gamma times image of S1. So if I have multiple wrappings, I can have here like LS1. And here I'm integrating omega ID, and I consider this omega ID depending only on xi, I less or equal to d minus 1. dxd. dxi. And I am able to take this integral to get L. And what is left is an integral over the image gamma omega ID dxi, I less or equal to d.
So this constant should imply some physical meaning.
You see wrapping, wrapping of the string is a charge of a particle.
Yeah.
So if string is charged under the 2 form, then a wrapped string is charged under this component, considered as a gauge field. So you see, today I was talking mostly about main characteristics, about charges and tensions. So for in ordinary particle physics, we have charges and mass. In this mathematical physics, we have generalized charges and tension. And we see what happens if an extended object is wrapped around a circle. It loses one of its dimensions. Its tension is multiplied by the radius. Times the number of wrapping. And what is interesting is that its charge is that the tensor charge becomes ordinary charge. That is proportional to number of wrappings. You just need to imagine.
So here, this L is just this integer L that just comes from this P1 of S1.
Yes, of
basically.
course.
And if our original object was not just S1 times gamma, say some Sn times gamma, we would be able to start seeing some, P1 of any Sn, I think.
Zero.
Yeah, but
But you are right. What Tim is saying? Tim wants to modify, and it could be modified. Suppose that we will do S2 times. So let's go from RD to S2 times RD minus P. Suppose we start with the two braids. These two braids would wrap over S2, and we will get a particle in RD minus 2. And these things are really happening in M theory. But I don't want to frighten you with that.
this is also not very interesting, right? Because P2 of S2 is also just
One.
no, I mean
P2 of S2
P2 of S2
is 1, is Z.
is Z.
Yeah.
So I was thinking of maybe some Pn of S2, where a lot of interesting and complicated finite groups start to
You
appear.
see, finite groups, unfortunately, you see here, so your question is even deeper. So I need to say that I don't know if one can find if you can study some delicate phenomena here. Probably yes. Probably yes. Probably working with duality, you can find something like this. I don't know. It's a good question.
What was the question again?
So that's what Tim was saying.
Yeah.
That we know that the rational cohomology.
Homotopy, not cohomology.
Yes.
Cohomology are zero.
Yes.
Rational homotopy groups for a sphere are non-trivial.
The rational homotopy groups for sphere are non-trivial. So what would happen if we will use branes that are wrapped according to these non-trivial homotopy groups? We will definitely get some branes in lower dimension. However, I need to say that these branes would be, so I'm sorry, now I need to say something professional, non-BPS branes.
So you mean that this will be bankrupt or like torsions?
Not only there will be torsions, there will be not BPS branes.
Yeah.
So I don't think that we would have control of them. But would we have some control of them? It would be interesting.
There are some works on BPS.
Yes.
Right. Yeah. But I don't know if exactly like that.
So So this example of Kim tells us how people are checking on it. You have this business, and then I will tell you that there is a main conjecture. And you use this main conjecture. You start with something, like what Tim says, compactification when you have these grains in one picture. And you try to see what does it mean in another picture. And in many cases, in another picture, answer is understandable. And then you take this understandable answer and go to mathematician and say, look, there's a new conjecture. That this equals to this. And then mathematician would write a long paper about it.
Sometimes.
Sometimes, if you are lucky. But Tim, you got the rules of the game. Wrapping is very important thing. Momentum expansion. And working with the objects of different dimensionality in different dimensions. So it was Kaluza story. So everything started at 1920.